Chapter 9, Steady-State Power Analysis, Sections 5 to 9. Our learning goals for Sections 5 to 9 are to consider the power factor, or a measure of the angle between current and voltage phasors, investigate complex power, or the measurement of power using phasors, power factor correction, or how to improve power transfer to a load by aligning the phasors with compensation networks, single-phase 3-wire circuits, the typical distribution method for households and small loads. Section 5, Power Factor. Here we have a typical load Z sub L with a current I sub M angle theta I, with the resulting voltage across the load V sub M angle theta V. We can plot the phasors I and V, and they have their matching angles theta I and theta V in some manner. V is equal to Z times I, or the angle V is also equal to the angle Z plus the angle of I, or theta V is equal to theta Z plus theta I. So theta Z essentially is the difference between theta I and theta V. If it is a capacitive load, then theta Z lies between minus 90 and 0. And if it's an inductive load, theta Z lies between 0 and 90 degrees with respect to voltage. Power is 1/2 V sub M I sub M cosine of the difference between theta V and theta I, or as we found in the last sections, VRMS, the root mean square voltage, times IRMS times cosine theta V minus theta I. Let's define the apparent power as just the product of VRMS and IRMS. Then we can define the power factor, or P sub F, as the ratio of P divided by the apparent power. That's equal to cosine theta V minus theta I, or if you will, equal to cosine theta Z. The power P then could also be written as VRMS times IRMS times the power factor directly. We don't even need to know theta V, theta I, or theta Z if we have the power factor. Here's a chart of the various values of the power factor and the resulting theta Z. If the power factor is 0, theta Z is minus 90. If the power factor is between 0 and 1, theta Z is between minus 90 and 0, indicating a leading or capacitive type circuit. If the power factor is 1, theta Z is 0. That's a purely resistive circuit, and current and voltage are collinear, as we've seen. If the power factor also lies between 0 and 1, it could be that theta Z lies between 0 and 90, indicating a lagging or an inductive circuit. And finally, if the power factor is 0, theta Z could be 90 degrees, which is purely inductive. Note that there are multiple definitions. For example, for the power factor of 0, we could have two different values of theta Z. That's because the cosine function is an even function. In this learning example, we want to find the power supplied by the power company and determine how it changes if we modify the power factor. So here we have the source from the power company, which is V sub S. The power company also has a distribution load of 0.08 ohms, producing a 480 volt RMS voltage signal across the load with a resulting IRMS current going through it. By measurement, we know that the power in the load is 88 kilowatts, or 88,000 watts. And by measurement between the angles between the current and the voltage, we find that the power factor is 0.707, lagging. That means that cosine theta Z equals 0.707, and theta Z then is minus 45 degrees. Of course, we need to know that it's lagging in order to put the sign for theta z as minus 45. The power then is VRMS times IRMS times the power factor. And IRMS can be computed. It's 88 kilowatts, 88 times 10 to the third watts, divided by 480 times 0.707. That's 259.3 amperes RMS. The losses, the power losses then in the load are IRMS squared times R. And in this case, because of the distribution load, it's 0.08 ohms. So that's a typo. It should be 259.3 squared times 0.8 is 5.378 kilowatts. The power then from the source includes these losses, plus the load consumption of 88,000 watts for a total of 93.378 kilowatts. If the power factor now changes to 0.9, we can redo the calculation. By substituting 0.9 for the power factor, we find that IRMS now decreases to 203.7 amperes RMS, down from 259.3. And the losses due to distribution are still IRMS squared times R, but now have been reduced from 5.378 kilowatts to 3.32 kilowatts. In other words, a reduction by 2 kilowatts. The comment here is that the power company still charges you for consumed power even through the distribution losses. So by changing the power factor, you can actually lower your costs by reducing your losses. Let's also examine the generated voltage. Current lags the voltage by definition. Therefore, we can draw a phasor diagram at 480 volts RMS with 259.3 angle minus 45 degrees as the current. V sub S RMS then is 0.8 times IRMS plus V sub L. That's just Kirchhoff's voltage law, working it back to the source, V sub S. Substitution of the values that we just found, and notice that we have mixed mode complex arithmetic with a phasor value and real values. We have to reduce that to rectangular form and then produce an answer which is either in rectangular form or in phasor form for V sub S RMS as 495 angle minus 1.7 degrees, even though the load is 480 volts. That's because of the losses. If the power factor is changed to 0.9, we can redo the calculation using the new value of IRMS that we just calculated, and we find that V sub S then is 494 angle minus 0.82 degrees. As this learning extension has, we have an industrial load that consumes 100 kilowatts at 0.707 power factor lagging. The 60 hertz line voltage at load is 480 volts RMS. In this case, the transmission line resistance between the power transformer and the load is 0.1 ohm. Determine the power factor savings that could be obtained if the power factor is changed from 0.707 initially to 0.9 lagging. Cosine theta z is the same as in the previous example. It's 0.707, and we have to know from its lagging representation that theta z is minus 45 degrees. Current lags the voltage again. IRMS can be computed. Now this is a typo, but the answer is correct. It should be 100 kilowatts divided by 480 times 0.707, the power factor, giving us 294.67 amperes RMS. The losses then are still IRMS squared times R. In this case, that's also a typo. It should be 0.1 ohm, but the number is correct. And therefore, the power provided by the source, P sub S, is the losses plus 100,000 watts, or 100 kilowatts, or 108.3683 kilowatts. If we change the power factor to 0.94, as the problem states, the numbers change. IRMS now goes lower to 221.63, down from 294. And the losses are still I squared RMS times R. R is also still 0.1 ohms or 4.912 kilowatts. And therefore, here we can reduce our losses by over 3 kilowatts, almost 4 kilowatts. Section 6, complex power. Let's define complex power. We'll define complex power and we'll give it a special value symbol S as opposed to P, and we'll call that VRMS times IRMS conjugate as the definition of complex power. In the circuit that we have here, we have VRMS across a load Z, producing a current IRMS. And of course, Z being a complex impedance, it has a magnitude and phase angle, and the phase angle is theta Z. Our new definition for complex power would be VRMS angle theta V times IRMS angle theta I, but its complex conjugate form. Therefore, S complex power is VRMS the magnitude times IRMS the magnitude at an angle of theta V minus theta I as a result. That's what the complex conjugate would indicate. Or S is equal to VRMS IRMS cosine theta V minus theta I plus J, since it's complex power, VRMS IRMS sine of theta V minus theta I in rectangular form. We'll call the first component, VRMS IRMS cosine theta V minus theta I, the active power because we've already identified it as the power P. And we'll call the second term, the complex part, we'll call it Q, the reactive power. So if you will, S is equal to P plus Q, the active power plus the reactive power. The units of a power and apparent and reactive power are called volt amperes, as opposed to watts, which we did for just totally active power with no reactive power. Volt ampere. So the magnitude of S is VRMS times IRMS. That's where we get the units of volt amperes. And the magnitude of S is nothing more than the power P times the power factor, because that includes the representation of the angle between the voltage and the current. We can plot it on a real and imaginary axis. We see, for example, IRMS. We see VRMS. We see IRMS cosine theta V minus theta I. Notice it is collinear with VRMS since it's active power. And we also have a complex conjugate term, or complex term, called IRMS sine theta V minus theta I, which is at right angles to produce the vector sum to the current IRMS, which is not collinear with VRMS. So again, if we plot the complex power S, we could see that if theta V minus theta I is positive, we have a term which is inductive as a result, and we have active power P along the real axis and plus Q, if you will, the reactive power pointing on the positive imaginary axis. And on the other hand, if we plot S as theta V minus theta I with minus Q, we have a capacitive loading system. So another useful form then would be VRMS is equal to Z times IRMS. Another useful form can then be used to reduce by using complex power. S then is equal to ZIRMS times IRMS conjugate. Well, the product of a complex number and its conjugate is the magnitude squared. So that's equal to Z times the magnitude of IRMS squared. That would give us VRMS. Z is equal to R plus JX. Loads are real and imaginary. And power then is R times the magnitude of IRMS. And Q, the reactive power, is X, the complex component, times the magnitude of I RMS squared. So these are all very useful definitions to manipulate and analyze problems. So here we have S as another example as being I RMS squared times Z, and Q being I RMS times the imaginary part of Z. And finally, active power P being I RMS squared times the real part of Z. For a resistor, of course, theta V minus theta I is 0, and cosine theta V minus theta I as a result is 1. Therefore, sine of theta V minus theta I has to be 0, and for a resistor, the reactive power Q would identically be 0. For an inductor, theta V minus theta I is 90 degrees. Therefore, there is an active power component, VRMS times IRMS times cosine 90, but of course cosine 90 means that the active power is 0, and the reactive power Q would be VRMS times IRMS times sine of 90, which is going to be greater than 0, obviously, because sine of 90 is 1. Likewise, for a capacitor, theta V minus theta I is equal to minus 90 degrees. The power still remains 0. The active power P still remains 0, cosine minus 90 degrees. And now we have Q, VRMS times IRMS times sine of minus 90, which is actually less than 0, which means that capacitors actually supply reactive power as a result, back to the source. Problem-solving strategy. If V of t and I of t are known, and we wish to find the power P given some impedance Z at an angle theta equal to R plus JX, two viable approaches can be followed. Step 1. Determine V and I and then calculate. P is equal to VRMS IRMS cosine theta, or if you will, P is equal to VRMS IRMS cosine of theta V minus theta I. Step 2, use I then to calculate the real part of S by saying that power is the real part, power P that we just calculated, is the real part of S is equal to I squared R. However, remember that P is not equal to V squared over R, especially if X is not equal to 0. Of course, P is equal to V squared over R in some situations, especially if X is equal to 0, and that would be called a DC circuit. So let's do a learning example to put these concepts into practice. Here we have a load, P sub L of 20 kilowatts, a power factor of 0.8 lagging. V sub L is 220 volts RMS with an angle of 0. And Z sub L is 0.9 plus J 0.3 ohms at a frequency of 60 hertz. We have a source V sub S, but this time the transmission system has not only a resistive component of 0.9 ohms, but also a inductive reactive component of J 0.3 ohms, producing a load current of I sub L. We want to find the voltage and power factor at the input to the line. Well, that's an inductive circuit as a result. We know that the complex power will be represented by P and Q, the inductive representation. P is equal to the real part of S, the complex power, and magnitude of S times cosine of theta V minus theta I is equal to the magnitude of S times the power factor. Q squared then is equal to S squared minus P squared. And we get, by definition then, that Q is equal to 15 kilovolt amperes. Notice the units are kilovolt amperes. There's a missing calculation here, of course, and that is the calculation that's shown as the blank blue box. So let me fill it in for you. So for example, we know that P is equal to, P sub L is equal to 20 kilowatts. And it's also equal to the magnitude of S times the power factor. Well, 20 kilowatts then would be equal to the magnitude of S times 0.8, or the magnitude of S would be 25 kilovolt amperes as a result. And that's the missing concept. That would be S sub L. So therefore Q squared, the reactive power squared, would be S sub L squared minus P squared, which would be, as a result, 25 squared minus 20 squared, or 625 minus 400. And then we would take the square root, and we would end up with Q is equal to 15 kilovolt amperes as a result. S sub L, since it's 50 given anyway, S sub L, the complex power, would be 20 plus J, 15 kilovolt amperes. We just solved for Q. Or if you will, 25 angle 36.87, which we also got by looking at the calculation that we just indicated. S sub L is also equal to V sub L, the load voltage, times I sub L conjugate. I sub L is then the ratio of S sub L divided by V sub L conjugate. Well, we know that S sub L was 25 kilovolt amperes, 25,000 angle 36.87 degrees, divided by V sub L, which is given as 220 angle 0. We perform that calculation, but we'd be very careful to do the complex conjugate. So basically, it's the magnitude 25,000 divided by 220, which gives us 113.64. And then when we take the angles in normal calculation, it would be 36.87 minus 0, which gives us plus 36.87 or so. And therefore, when we take the complex conjugate, we end up with the negative value, approximately minus 36.8786 or so. So that's how the complex conjugate is taken in the arithmetic calculation for I sub L. So substitution of the rectangular equivalent of I sub L, which is easier to handle for complex conjugates, we then can calculate I sub L in its, also we can calculate I sub L in its rectangular form. We already know it in its polar form, so we can go directly if we so choose. But in this case, in rectangular form, it's 90.91 minus J, 68.18 amperes for I sub L. V sub S then, as far as the source is concerned, using Kirchhoff's voltage law, would be the network losses, 0.9 ohms plus J 0.3 times I sub L. And we do know that the load voltage, V sub L, is 220 at an angle 0. Our only problem is to consider this as a complex arithmetic problem. We are helped by the fact that 220 angle 0 is already just 220 in rectangular form as a real part with no complex part. So we can perform the arithmetic by substituting I sub L in its rectangular form, perform the arithmetic calculation, and we can end up with these numbers for V sub S. As a phasor, 249.53, angle 4.86. As in all of these learning examples, you really do want to do the arithmetic yourself to verify your procedures and techniques. So we can plot V sub S at an angle of 4.86 and I sub L at an angle of minus 36.86 as a result, and therefore consider what the power factor is, because that's what was one of our predicates for this particular problem. It's the angle between the load current and the source, in this case 41.72 degrees, which is the total angle between those two. Be careful about the negative sign for the current because you're interested in the angle between. So in this case, we get 0.746, and we know it's lagging because the definition of I sub L has a negative angle, and therefore would indicate a lagging or capacitive circuit. In this learning example, we want to compute the average power flow between arbitrary networks and determine, in fact, which one is the source. Network A, we know, provides voltage VA at 120 angle 30 degrees, volts RMS. Network B has a VB across it, which is 120 angle 0 volts RMS. Between the two networks is a impedance Z, which is J1 ohm. And that produces a current I in the direction arbitrarily chosen as shown from A to B. And our concept now is to investigate which one is the source and which one is the load. They both can't be sources and they both can't be loads. So let's consider first the current I. I is equal to VA minus VB over Z. That's Kirchhoff's voltage law. 120 angle 30 degrees minus 120 angle 0 divided by J1. And of course, the problem here is that we have the difference of phasors, which we have to reduce to rectangular form in order to calculate algebraically. We can do that, and we end up with the result that the current I is 60 plus J 16.08 amperes RMS. Or if you will, I is equal to 62.12 angle 15 degrees amperes RMS. SA then, by definition, the so-called complex power for network A is VA times minus I conjugate. Now it's minus I because of our assumed direction of the current, and it's certainly conjugate because that is the functional definition of complex power, voltage times the conjugate of current. Substituting in the value of VA and the value of I that was just determined, but noticing that we must take the negative value and its complex conjugate as a result, we end up with 7,454 volt amperes RMS at an angle of minus 165 degrees approximately. PA then, the active or real power that results in network A, is 7,454 times cosine of 165, and we write it as minus 7,200 watts, not because of the cosine term, but because of the fact that we've noticed the angle has already been calculated. Therefore, we write minus 7,200 watts because of the way that we've calculated the complex power and the current that results from network A. Complex power for network B solves similarly, but of course now I is not minus I, but just I. So it's VB times I conjugate, and we get the same answer, but in its complex conjugate form, 7,454 at an angle of minus 15 degrees volt amperes RMS. For SA, the passive sign convention means that the power has been received by network A. PB then, the active power in network B, even though it's cosine minus 15 degrees, of course we really can't tell from the even nature of cosine, but we would write that as plus 7,200 watts because of the convention, how current is flowing, and the resulting complex powers. So this is actually incorrect. B supplies 7.2 kilowatts average power to A. In this learning extension, we want to determine the real and reactive power losses and the real and reactive power supplied. So we have a voltage source, V sub S, with a transmission impedance of 0.1 ohms real due to a resistor and J 0.25 ohms due to an inductor, producing a load current I sub L. And we, through measurement, know that the voltage across the load is 220 volts at an angle 0 degrees, RMS. Please note that it does not have to be 0 degrees, but that's what this particular problem shows. We have 40 kilowatts of active power with a power factor of 0.84 lagging. And of course, that tells us that we do have a capacitive load as a result. The active power P is the real part of the complex power S, or if you will, the magnitude of S cosine theta V minus theta I, or more conveniently in this case, since we know the power factor, the magnitude of S times the power factor. The magnitude of S sub L then for the load would be P divided by PF. 40 kilowatts, so we'll just write 40, but it is 40 kilowatts, 40,000 watts, divided by 0.84 gives us 47.62 kilovolt amperes, or 1,000 volt amperes. The magnitude of Q sub L, which we can solve by taking the square root of the magnitude of S sub L squared minus P squared, algebraically gives us 25,839 volt amperes for the magnitude of the so-called reactive power. Magnitude, though. S is equal to V times I conjugate, therefore the magnitude of L, I sub L, would be the magnitude of S divided by the magnitude of VL. If that's all we're concerned about at the moment, we get 216.45 amperes RMS. The power factor we know is cosine theta V minus theta I. Therefore, theta V minus theta I is 32.86 degrees. Since we know the power factor is 0.84, we take the arc cosine. Here we have a representation of what's going on in the network. We have VRMS, we have IRMS cosine theta V minus theta I, which is the real power, the active power. Then we have IRMS times sine theta V minus theta I, which is the reactive power, giving rise to IRMS as a vector. I sub L, we have the magnitude, but we can now calculate the angle. I sub L is 216.45 at an angle of minus 32.86 degrees amperes RMS. For the losses, the complex power in the losses, we would get the impedance of the line times I sub L conjugate, or if you will, the impedance of the line times the magnitude of I sub L squared, because I sub L times I sub L conjugate is the magnitude squared. Therefore, the complex losses, S sub losses, would be 0.1 plus J 0.25 as a quantity, multiplied by 216.45 squared, producing an answer of 4685 plus J 11,713 volt amperes. For the balance of power, then, we know that the complex power supplied has to equal the complex power in the loss plus the complex power in the load. We can add up those quantities because we've calculated them, and we end up with the rectangular representation of the complex power is 44.685 plus J 37.552. Both of those units, though, are in kilovolt volt amperes. Another learning extension problem, determine the line voltage and power factor now at the supply end. Here we have V sub S is our arbitrary source, 0.12 ohms, and plus J 0.18 ohms. Inductive is our transmission system, 220 volts angle 0. Again, the comment about being angle 0, but yeah, that's what's given. 60 kilowatts for the active power with a power factor of 0.85 lagging. P is equal to the real part of the complex power. S sub L, then, it would be V sub L times I conjugate, I sub L conjugate. The magnitude of S times cosine theta V minus theta I would be the magnitude of V sub L times the magnitude of I sub L times the power factor. Or the magnitude of I sub L could also be found by taking the power P and divided by the magnitude of V sub L times the power factor, and algebraically we end up with 320.86 amperes RMS for I sub L, the magnitude of. Again, similar type of representation that we had in the prior example. Theta V is equal to theta V minus theta I is equal to the arc cosine of the power factor, as in the prior example, but in this case gives us 31.79 degrees. I sub L, that is 320.86, which is what we got for the magnitude, but now we have the phase angle as minus 31.79 degrees amperes RMS, And we can reduce that from polar to rectangular form, 272.72 minus J 169.03 amperes RMS. V sub S then is Z line times I sub L plus VL. That's Kirchhoff's voltage law for around that particular loop. We could substitute in what we know for Z line IL and VL. Conveniently, VL is just wholly real. And therefore, V sub S is 284.61 at an angle of 5.81 degrees, volts RMS. The phasor diagram helps us visualizing the relationship between voltage and current. We see V sub S at an angle of 5.81 with respect to V sub L, and I sub L with respect to V sub L is minus 31.79. So the overall power factor of the source, as opposed to the load, would be the angle between V sub S and I sub L. In this case, a total of 37.6 degrees, or a power factor of 0.792. And since I sub L is lagging V sub S, it also lags V sub L. That would indicate that it is a lagging power factor. This is section 7, power factor correction. Power factor correction. Low power factors increase losses and are penalized by energy companies by charging more. Typical industrial, or in fact even residential loads, tend to be inductive because of the preponderance of motors and rotating machinery that we might have. The simple approach then to power factor correction is to add a capacitive load which will adjust the power factor. So here we have an example of a generator providing load current to a load which is primarily inductive in nature, has some series resistance and some inductance with a voltage across it, and we will put a shunt or parallel capacitor, hopefully, to mitigate the power factor. If you look at the vector diagram, Q sub L is going to be mitigated by adding some quantity of negative reactive power, Q sub C, and hopefully those things will cancel at some point, and or at least reduce the power factor, if not cancel it entirely. So without a capacitor, the complex power without a capacitor, we'll call it S old, is equal to P old plus JQ old. That's the magnitude of the complex power old at an angle of theta old, and the power factor would be the cosine of theta old as a result. V sub L, of course, with a shunt capacitor in parallel, would be 1 over j omega c times the current that flows through the capacitor. The reactive power in the capacitor would be the magnitude of V sub L times the magnitude of the current that flows through the capacitor. Substituting the definitions, we would get that the reactive power of the capacitor would be the magnitude of V sub L squared times omega c. Notice the use of omega, that was part of the reactance of the capacitor, and that therefore is a function of frequency also. Without the capacitor, we had the power factor was just a cosine of theta old, but with the capacitor we've added a new term. So the complex power new is the complex power old plus the complex power due to the capacitor. So P old plus JQ old minus JQ capacitor, if you will. And that gives us the magnitude of S nu at the angle of theta nu, and a new power factor results. Hopefully the angle decreases, and therefore the power factor approaches 1. The tangent of the new theta nu, would be Q old minus Q capacitor divided by P old. That's our functional equation. And therefore cosine theta in general is a trigonometric identity, is 1 over the square root of tangent theta squared. We must keep trigonometric identities as part of our analysis tools, and we will use that in order to solve problems. In this learning example, let's look at the economic impact of power factor correction. It is common for an industrial facility operating at a poor power factor to be charged more by the electric utility. Let's take these as typical operating conditions. 277 volts RMS, requiring 500 kilowatts of real or active power at a power factor of 0.75 lagging. The energy charge would then be 2 cents per kilowatt hour. We call it kilowatt hour because energy is charged not only in watts, but also in the amount of time that the demand is. That's why it's kilowatt hours. And a demand charge of $3.50 per kilowatt per month if the power factor is between 0.9 lagging in unity, and $5 per kilovolt ampere per month if the power factor is less than 0.9 lagging. So the current monthly bill would be 500 kilowatts times 24 hours in a day times nominally 30 days in a month. Some months have 31 or 28 or 29, but let's use 30. Times 2 cents gives us $7,200 for the monthly energy charge. So the complex power S old would be 500 divided by 0.75 at an angle of the arc cosine of the power factor of 0.75, which would be 666.67 at an angle of 41 degrees. And that would be in kilovolt amperes, as it turns out, because it's kilowatts to begin with. And that's equivalent to 500 plus J441 kilovolt amperes. So therefore, the monthly demand charge would be that magnitude, 666 kilovolt amperes times $5 per kilovolt amperes per month. So the monthly demand charge on top of the energy charge would be $3,333.35 or so. If we change our power factor from 0.75 to 0.9, we can redo the calculation. We find that the complex power S new would be 500 divided now by 0.9 times at an angle of the arc cosine of 0.9, or 555.6 at an angle of 25.84 degrees, and that of course is again in kilovolt amperes because 500 is in kilowatts, which gives us 500 plus J242.2 kilovolt amperes. The new demand charge, though, because we've done our correction just barely with 0.9, would be 500 times $3.50, which would give us $1,750 per month. So that's down the demand charge from over $3,000. So the additional energy charge due to the capacitor bank is negligible if the capacitor has very low losses. The monthly saving of approximately $1,853 per month. And a reasonable capacitor bank, if you go out and purchase it and install it, should pay for itself in the savings of the energy bill in about a year. In this learning example, let's take a frequency of 60 hertz and determine the capacitor required to increase the power factor to 0.95 lagging. So we have some sort of a rotor molding process with an induction motor driving it. It's 50 kilowatts at a V sub L load voltage of 220 angle 0 RMS with a power factor of 0.8 lagging to begin with. P is equal to the real part of the complex power S, or the magnitude of S times cosine theta V minus theta I, or the magnitude of S times the power factor. Therefore, S old, magnitude of S old, would be P divided by PF. 80 kilowatts divided by 0.8 gives us 62.5 kilovolt amperes, since it's complex power. The magnitude of Q old, then, we've done this before, can be found by taking the square root of the magnitude of the complex power, S old squared, minus P squared, and the answer is 37.5 kilovolt amperes. Cosine theta nu, then, is supposed to be 0.95, therefore tangent nu would be 1 minus the power factor nu squared divided by the power factor nu. That gives us 0.3 ch09 as the expected tangent of the new angle theta, which is also equal to the complex power representation q nu divided by the active power p. So therefore q nu would be 0.329 times p, or if you will, 16.43 kilovolt amperes, an alternative way of calculating that using the expected value of the power factor as an angle. So the complex power in the capacitor would be Q old minus Q new, or 21.07 kilovolt amperes. We can now calculate what the capacitor might have to be in order to meet these particular requirements, and we're doing that from the power representation. We know the complex power in the capacitor now. Q capacitor is the magnitude of V sub L times the magnitude of the current flowing in the capacitor, I capacitor, but that's also equal to the magnitude of VL squared times omega C, as we've seen. So therefore, solving for C, we do know that omega is 2 pi f, 2 pi 60 in this case. We know the complex power in the capacitor, 21.07 times 10 to the third, or kilovolt amperes, divided by 220 squared, the magnitude of V sub L squared, times omega, which is 2 pi times 60. And we find that the value is 1,156 microfarads for the capacitor. Another learning extension: determine the capacitor necessary to increase the power factor to 0.94. We also know now that P sub L as given is 100 kilowatts, V sub L is 480 volts RMS. Power factor is 0.707 to begin with. The resistance of the transmission system, the R line, is 0.1 ohms at a frequency of 60 hertz. P is equal to the real part of the complex power S, or the magnitude of S times cosine theta V minus theta I, or equivalently and easier to calculate now, is the magnitude of S times the power factor. Solving for the magnitude of the complex power old, S old, we get P divided by PF. We've seen that formula before, or 100, in this case 100 kilowatts, divided by 0.707 gives us 141.44 kilovolt amperes. Please notice the units are volt amperes because it's complex power. The magnitude of Q old is the square root then of S old squared minus P squared. Substitution of the numbers we have give us 100.02 kilovolt amperes for the magnitude of Q old. So cosine theta nu, by definition, has to be 0.94. That's the power factor. Implies that the tangent of theta nu is the square root of 1 minus the power factor squared of the new value divided by the power factor nu, and that would be, as a result, 0.363, again from trig. 0.363 is Q nu divided by P, which implies that Q nu is 0.363 times P, or 36.3 kilovolt amperes. The Q capacitor is Q old minus Q new, 100.02, again these are all in kilovolt forms, thousands forms if you will, minus 36.3 is 63.72 kilovolt amperes. Q capacitor is also a magnitude of V sub L times I capacitor, or as we've seen, the magnitude of V sub L squared times omega C, which allows us to calculate for C. Substitution, of course, what omega is equal to, which is 60 hertz. So it's 2 pi times 60, and we get a value of the capacitor for this particular learning extension as 733 microfarads. This is section 8, single-phase 3-wire circuits. Power circuits normally used for a residential supply have this particular configuration. We have two voltage sources producing a line called A and a line called B and a line called N. N would be given the description of the neutral or the common return. This is a single phase 3-wire circuit as a result. Line to line used to supply major appliances. So for example, if I go from A to B, I could use that as a summated value of the two voltage sources to provide things like an air conditioner, an electric dryer, or something like that. We can also go from A to N, line to neutral, or from B to N, line to neutral. That would give us nominally 115 volts or so for common lights and small appliances. So that's what our basic circuit in our home might look like. We might have loads across the two different systems, the A system, the B system, with a neutral return. And of course, those Z sub-Ls do not have to be equal. They are just nominally there as the loads on these particular lines, called phases. We have circulating currents in each one of these cases. They don't have to be equal because the loads are not equal, but they do return through the neutral. If the loads are in fact balanced, perfectly balanced, the neutral current is 0, which is why it's often called the neutral. But in many cases, the lines loads, the two different Z sub-Ls in line A and line B are not equal. But if they are equal, then the currents basically are in opposite directions, as you see here, and they would actually subtract, and the result would be 0 neutral current. So for the balance case, we end up with a real situation where we have a Z line in each case, and also an impedance for the neutral return, Z sub N. And we have our load, ZL, ZL, for our two different phases. And then we also have our load, ZLL, which is across the phases, say, between A and B. So here we have an exercise in symmetry as a result, trying to produce a balanced situation for neutral current. The general case can be done by source superposition, which is the easiest way to solve this. And we can shut off one source at a time by general source superposition and solve the two networks that you see here on the lower right as a result. The concept here would be to have neutral current to be 0, which means that the current in each case by superposition would actually be equal and opposite in sign, and therefore produce 0 neutral current, I sub D in this case, but I sub N, the current through the neutral. All right, as a learning example, let's try this problem. Determine the energy use over a 24-hour period and the cost if the rate is 8 cents per kilowatt hour. So we have 120 angle 0 as a source in both the A line and the B line, 120 angle 0 and the B line also with the neutral return. We have lights which are producing 120 watts of load. We have some sort of a stereo producing 24 watts of load. We have an electric range which is running, which is 7,200 watts, and we'll call that I sub R for the current through the range. And we'll take a look at what the particular loading situation is, I sub L for the lights and I sub S for the stereo. We have the current in the A leg, A sub AA, and the current in the B leg, I sub BB. And we also have I sub NN in the neutral. We're going to assume that all the loads are in fact resistive, although that may or may not be generally true, but that makes the problem at least somewhat conceptually easier to begin with. The power P then is VRMS times IRMS. Lights are on. We end up with 1 ampere RMS because we have 120 volts RMS with 120 watts means that we have 1 ampere of current flowing here with the lights on. And with 120 volts and 24 watts, we take 120 divided by 24, we get 0.2 amps RMS if the stereo is on. The range then would consume 240 volts at 7,200 watts. That'd be 7,200 watts divided by 240 volts, or 30 amperes RMS, which is quite normal and nominal for an electric range. So we have a situation where the lights could be on or off, the stereo could be on or off, and the range could be on or off. And that's shown as a load diagram here versus a time axis in hours, if you will. And we're going to use this as a metric for computing what the actual cost might be. Energy is the integral of the power dt, or if you will, the average power times the time. So the energy in the lights is 0.12 kilowatts, which is 120 watts, which is 0.12 kilowatts, times 8 hours, because we've looked at the graph and we've determined that it has 8 hours on, plus another term in which it's 7 hours on. So we end up with 1.8 kilowatt hours for the lights. The energy for the range, 7.2 kilowatts, and the range is only on intermittently, but a total of 4 hours, or 28.8 kilowatt hours. The energy for the stereo, 0.24 kilowatts, times a total of 8 hours on, 0.192 kilowatt hours. Adding them up, we get 30.792 kilowatt hours, or a cost of $2.46 a day for this particular situation. We can verify the calculation. We can use Kirchhoff's current law to look at the different currents that are flowing. We can then look at E supplied equals the integral of P supplied, which would be VRMS times the integral of IRMS dt, because V is not changing, but I is certainly time varying as different elements turn on and off. So you can also perform this calculation from the load point of view, from the supplied point of view. You might want to try that. Safety considerations, section 9. Average effect of 60 hertz current from hand to hand and passing through the heart could be quite difficult to survive. We could have ventricular fibrillation, usually fatal, unless there's intervention. Required voltage depends upon the contact, the person, and other factors. So we do have to be careful about producing a current path across especially even typical line voltages at 120 volts RMS. If we have grounding, though, we have increased safety due to grounding. When switch on the tool case is energized, we can have conduction to the wet floor if we've lost our connection to our normal ground, but have connection through, for example, a concrete floor, which returns to earth ground. So as you see here, the person provides a path for current to return to the voltage source, which is a safety consideration for electrocution in this case. Without the ground connection, the user can be exposed to the full line voltage due to the concrete or wet floor that the person is standing on. If the case is grounded, then the supply is shorted and the fuse acts to open the circuit as a result. The fuse is that little element on the upper left next to the power supply that sort of looks like a half sinusoidal waveform. That's the symbol for a fuse. We could do more detailed numbers if we take a look at a related case study. A ground fault interrupter, which appears in many industrial and residential environments, hopefully provides some degree of protection. It's called the GFI. In normal operating mode, two currents induce canceling magnetic fluxes as a result. No voltage is induced in the sensing coil, and if I1 and I2 become different due to a fault in the load, then there's a voltage induced into the sensing coil, and the sensing coil essentially interrupts the circuit. That's why it's called a ground fault interrupter. So here's an example of that. We have a circuit breaker or fuse. We have the so-called hot or black wire. You might want to know that in electrical parlance, unlike many instrumentation cases, the black wire is in fact what is considered to be the hot or the potential bearing wire. The white is in fact the neutral wire, and often the ground is green as the ground return. If for some reason the ground prong on a device like a drill is either broken or removed, then we end up with a situation like this, where a short between the windings of the drill and the drill case can produce a current path through the body, our body, back through the unintentional ground, and that causes electrocution. Typically, the resistance of dry skin is about 15,000 ohms. For wet skin, about 150 ohms. The resistance of a limb, about 100 ohms. And the resistance of your thoracic body or your trunk is about 200 ohms. So basically, we can consider this as the path, if you will, through the skin, touching the drill case through the body, and then through the skin again to ground, and include the resistance of the nominal resistance of the limbs or the trunk, and the ground return of about 1 ohm, usually quite small. The current then through the body would be 120 volts nominal for the residential electrical supply, divided by a total resistance of about 701 ohms, about 171 milliamperes, if you will, and that it puts us in the range for causing ventricular fibrillation. Here's a ground fault scenario. When the boy is alone in the pool, there's no ground connection. In this case, the vinyl lining acts as an insulator, and there is in fact a ground fault. So there has been a problem. There's a light in the pool, which causes the problem. When the boy in the water touches the boy holding the grounded rail, we do have a path now, and we have a path for current to flow as a result, which can cause the particular problem in this condition. Assuming a fault, the pool and the railing resistances are approximately 0, and we end up with a current of about 126 milliamperes. In this learning example, we'll see what can happen in a clinical situation for accidental grounding. Here we have a patient that's being subjected to muscle stimulation, usually having to do with problems in locomotion or transit of the limbs, by a muscle stimulator, and the only return path in normal operation is through the muscle stimulator. However, at the same time, to monitor the state of the patient, we also have a EKG or electrocardiogram monitor, and that will cause a problem because it is defective. So we have new path created by the grounding of the electrocardiogram, which may in fact be defective, and therefore we have a situation in which we have current that could flow through the arm, the trunk, the leg, producing a return path other than the muscle stimulator, in this case through the body, which will cause possible electrocution. We end up with a body current then of about 19 milliamperes. And the suggested value of resistance, the secondary path causes a dangerous current then to flow through the body. This is usually monitored quite intensely in a clinical environment by clinical engineering, which is a division of a hospital that makes sure that the monitoring equipment does not cause particular problems, especially in operation. Another learning example, a grounding accident. Unfortunately, this happens a lot. We have a power line, a neutral conductor, a power line, and another power line. And we have a device, maybe like in this case it shows some sort of a crane, which goes along and happens to touch the 7,200 volt power line and provides an alternative path to ground as a result, which is through the crane. After the boom touches the live wire, the operator jumps down and starts walking towards the pole. The ground is not a perfect conductor. However, it does have sufficient resistance to cause a problem between the crane, the earth resistance, and the power pole. And therefore, at 720 volts per meter, 10 meters, 7,200 volts, 720 volts per meter, each step applies 720 volts to the operator as a result. A 7,200 volt power line falls on a car and makes contact with it. We have a wet road, we have a car. Nice looking car too. Option 1, driver opens the door and steps down. Option 2, driver stays inside the car. So the question is, which one is better? Car body is a good conductor. As a result, we have our typical values for dry skin, wet skin, limb, and trunk, suggested resistances for the car body, for the human body. We can then calculate what the current through the body would be, 7,200 volts under option 1 if the driver opens the door. We would have about 460 milliamperes, extremely dangerous. So opening the door and stepping down provides an alternative path to ground through the wet road. If you stay inside the car, the current through the body is 0, and therefore you should have much better effect waiting for qualified personnel to come to mitigate the situation. So if something like this does happen, stay inside the car. With that, we have the end of Chapter 9, Steady State Power Analysis, Sections 5 to 9.